All right, so welcome back to calculus, and let's continue with our topics on limits. So last lecture, I was going over how we can numerically estimate or predict a limit on any function. And so what we are doing here in this lecture is we are going to investigate, or we are going to study the graphical interpretation of those limits. So here, particularly in this topic, let's say we're going to give some graphical, we're going to have a graphical understanding. Okay, so we're going to be looking at the graphical understanding, the graphical interpretation of those limits result. All right, so the plan for this lecture in particular, I am going to repeat almost all of the examples I've gone through in the earlier lecture. So any example, most of the examples from the lecture where I was doing numerical approach, where I was doing numerical estimation on the limits, I'm going to repeat most of those examples here, but with a graphical explanation here of the result. So let's start out with that. Introduction problem. So the introduction problem in our earlier lecture, we were looking at, let's say we had a given function f of x being defined to be 2x minus 3. So once again, our function given here is being a function f of x being 2x minus 3, and along it had a given point. So this, besides having a given function, we also had a given point at x equals 2. And so all those terminologies we have picked up throughout the earlier lecture right before this lecture, we refer to this point here as the limit point. So that's just a reminder of all the terminologies, making it convenient for good communication among all the mathematicians out there. So this is, once again, after our last lecture, we learned that this point here is being referred to as the limit point. Okay, so anyone viewing this video or anyone being in a calculus level course is expected to know how to graph a function like this. And so I am not going to show how to graph, but instead I am going to use my computer simulation. I am going to use my computer program to instantly bring up the graph here. And if you're really not sure how the computer generated a graph like those, you can see me outside of class, or you can contact me in person to get some explanation. But this function here is simply a linear function, slope 2 and with y-intercept minus 3. So on my computer screen right here, and by the way, throughout the entire quarter of calculus, a lot of time I am going to be using decimals for a lot of my graphical demonstration of the concept right here. Okay, so 2x minus 3 as our current function has this graph right here. So everybody already knew it's a linear function. So quickly, let me put it in this form right here. But it's a linear function, so it's having slope 2, and it's having y-intercept being negative 3. And so that is the reason why, if you're looking at closely into the graph, and by the way, the red line right here is the actual graph. This red line, as my mouse is pointing to, is the actual graph of our function 2x minus 3. So f of x being 2x minus 3 is being graphed by the red line. For now, don't be too concerned about what these green lines and these fancy points are all about. But so, according to the information, so now let me put the two screens together. But so, according to the given information, our limit point is being x equals 2. And so that is the reason why on my graph right here on the x-axis, I'm simply putting one point, one singular point on the x-axis, being x equals 2 is right here. And notice, remember, as we finished with the earlier lecture, I already mentioned that we don't need to worry about plugging in this x equals 2 into the function. And so for that reason, there won't be, I don't have to worry about what's the height of this x equals 2 on the graph. I don't need to worry about that particular point on the graph. I only need to simply treat x equals 2 as one point on the entire x-axis. So the entire infinite x-axis is here. Okay, and so what we study here is that we break it down in our earlier lecture. For this first limits problem ever, then we broke it down into two separate approach, two separate tables of values. So the first one was we were trying to describe that we're approaching x values, getting close to 2 from the left-hand side. So this is my demonstration right here. So let's pretend that we have a starting point here somewhere on the, and maybe let me put it in a closer zoom right here. All right, so here we go. So hopefully now everybody is having a nice clear view with this zoomed in version of my graph. But so at some point to the left of the limit point x equals 2, so at some point to the left, okay, now this point currently is not x equals 2, so we have our right to substitute that into the function, and here we have a height. So the height here is a negative height, and it's being indicated in green. Okay, so the vertical height for these points are being represented in green with the graph that I purposely set it up that way. But now let's make the observation. The idea now is that we are letting this point, we're letting x value getting close to 2. So now go ahead and observe. So as my black point is representing a value on the x-axis getting close to 2, so that's why I'm navigating. So notice the change of the green line right here. The height becomes less negative, and past a certain value for x, it's gonna becomes a positive height, and it keep increasing. So I'm still talking about the green line right here. It's now keep increasing height as our black line on the left-hand side of x equals 2 is getting closer to 2. But everything on the horizontal movement of my point here is from the left-hand side of x equals 2. So once again, I'm trying to describe the fact, to illustrate the fact that we're getting close to 2, but from the left-hand side. Okay, and so as I continue to go, and even let me move in a little further. I'm not too satisfied with the way how they look right now. So as I'm getting closer to 2 with my black point here, getting closer to 2 from the left-hand side, notice how the height keep changing, how the height keep increasing, the height in green keep increasing. And so now I'm at pretty close. You see that that little point right there is pretty close to x equals 2. But remember, we won't be at x equals 2. We are only getting closer. But as I keep getting closer and getting closer, the height here seemingly this green height keep making some attempt to hit to a certain height. And so that certain height here, now you don't need to worry about anything fancy being on the board here right now. But now let me display. So now the reason I put this horizontal line is being at y equals 1, but I'm not intending for this height to be the height of the function at x equals 2. It happens to be, but simply this height is the height that seems like the vertical green height is making attempt to get close to. All right, so once again, let me repeat. We are from somewhere far away. We are from somewhere far away from x equals 2. And then our black point is getting closer to 2. So the green height is making its way, is making its attempt to get close to that height being y equals 1 right here. And that's the reason why back in what we explained earlier, then we had that understanding that this same function 2x minus 3, as we took the limits, but that was taking x value closer and closer to 2 from the left-hand side. Okay, then we agree that the limits there, that height, the height in green that you've seen in your graphical illustration, it came to 1. And so that was the left-hand side demonstration. So in the meanwhile, so now let me put this a little bit down right here. And maybe a little bit smaller zoom, further zoom. All right, and so in the meanwhile, back to that very introductory example, then I also had a table describing values of x getting closer to 2 but from the right hand side. So this is what the other black point on the right hand side of the blue point 2 right here. Let me move this point a little further out so we have more space for this point to come in. But so this point here, pretend that it's some starting point being to the right hand side of 2. And now the green height right here, and keep in mind again, x equals 3 is not x equals 2, so we have our right, we have our freedom to substitute it into the function. And that's how I've had these vertical heights right here. And now observe the motion of the value on the x-axis as I'm letting my black point getting closer and closer to that limit point x equals 2, then notice how the green height is being decreased. Okay, and it keeps decreasing. It keeps decreasing. But it seems like as I keep making my x values closer and closer to x equals 2, and you can see that my label here is indicating now I'm at x equals 2.09, still to the right hand side of x equals 2, but pretty close. But then as I keep getting closer and closer, right, my green height seems to make its attempt to get close to this vertical height again, which is the height y equals 1. And so in that argument, now allow me to get back to my board again. But that's why here under a graphical interpretation, then the same function 2x minus 3 as our function f of x. But it had a limit as x getting close to 2, but from the right hand side, okay, it came to the limit equals 1. So the vertical height shrink down to 1. And so for that reason, okay, so now left hand side limit when x came to 2 from the left hand side on the same function 2x minus 3, we found our limit was 1. And so left hand side limit and right hand side limit agreed. And in my explanation I delivered back in that earlier lecture, then this was the reason why I had 2x minus 3 as our function. But as we were finding the limits of this function when x getting close to 2, but generally from both sides. Now in this third line right here, I'm skipping that superscript indication. Then that limits overall agree to 1. And that's the reason why you can see, so generally from both sides, either from the right hand side, okay, or from the left hand side, both green lines from the left and from the right seems all to both making its way to that line, to that dotted line y equals 1. All right, and so that is an interpretation, a graphical explanation of how we've had this and how our conclusion back in the earlier lecture agrees with the graphical interpretation of that. Okay, so once we're done with that, introductory example or problem, then after talking about some theory and giving definitions of what a limit was, I started into example 1. So we are not going to redo example 1, but now we're going to restate example 1's result. So example 1 here, I am not going to repeat all of those, but at least let's look at the problem in part A right here. We were looking at our function here in example 1a was being an x squared function. And the problem wanted us to find the limits of this problem as x was getting close to -1. So -1, keep in mind -1 was our limit point on the x-axis. And notice the problem did not indicate any superscript. So this is a general two-sided getting close to -1 from both sides. And so our answer was +1. But now let's find out, let's see how the graph of this x squared function agrees with this limit problem. And so here, back into my graph. This is the graph for my x squared function. It's the famous x squared function. Anyone taking the math as high as calculus is well familiar with this graph right here. It's a nice parabolic shape and having its vertex right at 0, 0, the origin. But so the limit point is -1. The limit point is -1. So that's why I leave that -1 right here on the x-axis. And once again, in a very similar interpretation, I don't need to worry about where that particular point is on the graph when x equals 1, because that's not the point. We never had to plug in x equals -1 into the function. But what we do now, once again, if we were approaching, and now after my explanation in the earlier lecture, then anytime that we are doing a limits problem like this where there was no specific indication about which side we were approaching, then it was our responsibility to know that we gotta first consider the approach, consider the fact that we're letting x value coming close to this limit point -1 from the left hand side, and repeat the process getting close to -1, the limit point from the right hand side. So the two processes there, are automatically our responsibilities for getting that done. And so getting back on my screen right here, okay, and then so all right, so now on the left, from the left hand side, my black point is getting ready for getting close. So right now back in my example that I did in the example in the earlier lecture, I believe I started out with x equals -2. Then I came closer to -1 from the left hand side. So -2 is on the left hand side of -1, and now I'm getting closer. So notice my green height is losing its own altitude, is losing its own height right here. But then seems like it's making its way as I keep getting closer. And by the way, let me zoom in a little better so that we have a closer view of the story here. But as I'm getting closer on the x-axis here, as I'm getting closer to -1, but from the left-hand side, and it seems like my green line is making its attempt to get close to a certain horizontal height right here. I mean vertical height. And so that vertical height, now I put that visible here. It looks like it's making its way to get close to y equals 1. Okay? And so from far away, and now getting closer on the x-axis, getting closer to -1. And so as our green height is keep dropping, but it's not going to go anywhere further than 1 or down below 1. And so now I can make my explanation, I can make my interpretation that this same problem allowed me to erase that out and rewrite it here. But on the x square graph, on the graph of x squared here, its limits as x was getting close to -1, but from the left hand side, that was my graphical interpretation earlier. We found out that it looks like graphically describing that the height there was getting close to 1, and that was our limit as x getting close to -1 from the left hand side. And again, from the right hand side, let me now move this point a little further out so that we can see some better space and better viewing. But let's say start out with x equals 0 on the x-axis, and now we're getting closer. Now right now, when x equals 0 as a value, then our height is 0, and everybody knows that. But now as I'm getting closer to -1 from the right-hand side, so hopefully everybody see the motion of my black point on the x-axis here. It's getting closer to the limit point, but everything now is from the right-hand side. And so as we keep getting closer to the right-hand, to -1 from the right-hand side, then we're going to keep getting more height. The green heights here keep getting better and keep getting higher and keep getting higher. It keeps getting higher. But seems like no matter how high it gets, it's just going to right about hitting that line y equals 1 again. And remember, my aim here is not to I'm not aiming to explain that the y equals 1 is the point on the graph. It's there or it's not, that doesn't matter, because we never substitute the blue point. We never substituted x equals -1 into the function. But what we did here is that we substituted these values near -1 into the function. That's how we obtain these points right here with vertical height. But now, as I keep getting there and I keep getting closer, and so it seems like my prediction here, it seems like graphically our height is hitting to that dotted height being 1. And so once again, back on my board, the same function x squared, but as we were letting x getting close to -1 from the right hand side, that's why I had this little superscript plus sign here next to my limit point. Then the limits of this function, the height of this function seems to get close to +1 as the height as well. And so now once again, so right hand side, the vertical height came to 1. Left hand side, I wrote it down earlier and I had to erase it to make space. But now the limit from the left hand side, when x gets close to -1, but from the left hand side, that limits, the height there also came to 1. So left limits and right limits both agreed again. And so in that way, our final conclusion here, which agreed with how I explained that in the earlier lecture. So now the limits of our main problem was asking for the general limits when x getting close to -1, generally from both sides. That limits there was also 1 as well. And that was our problem for that. Okay? And then after this problem, I went over to example 2. And so in example 2, we had our function being 1 over x squared. And once again, with this function, we want to find the limit of the function 1 over x squared as we were letting x coming close to 0 generally from both sides. Okay. And so let's look over to the graph of 1 over x squared. Now, I don't blame anyone that you don't remember the graph of this 1 over x squared, but I can quickly pull up the graph on the screen here. But if you're not sure, make sure you review your algebra for that, because even back in algebra, there were not too many times that we were looking at the function like this, 1 over x squared. Okay, so that's not the one yet. Here's my graph for 1 over x squared. So this is the graph for 1 over x squared. So if you recall from your algebraic understanding that this function has a vertical asymptote here. And you can already see that this the kind of nature that as we're getting closer and closer to 0 on the x-axis here, then the graph keeps rising up. And as a matter of fact, that's where I'm going. And so let me show the two screens together again. All right, and now in a closer zoom. All right, let's find out what happened. And it is now, when we get into this kind of problem, it is extremely and critically important to understand that we should never plug x equals 0 into the function. So as a matter of fact, the domain, if anyone being unsure about what the domain I'm talking about is, review your algebra. You got to constantly review your algebra when you're doing these kind of calculus work here. But the domain of this function is going to be any x value except 0. So this function is okay to take any value for x except x equals 0. So I have to clearly indicate that is the reason why we never had to worry about plugging in, because the limit is not about plugging in. Limit is just about getting close to 0. I mean getting close to the limit point. And so our limit point is being quite critical. We cannot plug it in. But now we're going to get close to it from the left-hand side and from the right-hand side. And let's find out what's happened to our function here, to our limits overall. And so on my screen here, from the left-hand side, I'm getting closer. I'm starting with x equals -2, maybe a little bit different with how I lecture. But now I'm getting closer. And so notice how my heights keep getting, how my green heights keep getting as my black point indicating an x value getting closer to 0. As I'm getting close to 0, my height keep rising, and you can see how it keep rising. And so maybe a little further zoom so that you can, let me zoom out a little further so you can see more about how the height rapidly grows right here. The green height growing fast and growing fast. Now it's not really leaving the graph, it's just too high so that, you know, when I have to pull it further out, and you're gonna see where it hits the graph like that. But so that's how, okay, so as I keep making my way on the x-axis closer to 0, but from the left-hand side, right, the height keep growing up and keep growing up. And that was, so these heights here seems to keep growing infinitely. And that was the reason why, back in the lecture we've had earlier. So now, wrapping it up, this same function, when we were letting x value coming close to 0, but from the left-hand side, as just now I illustrated with the graphical interpretation, then the vertical height seems to keep rising and rising and rising, you know, unboundedly. So positive infinity is the best way to describe the situation we have here. And then again, that's only halfway of the story. And so on the other hand, so now let me move this point further out. From the right-hand side, let me now, let's say starting with x equals 2, and you can already see a little bit that there's a little bit of green height right here. But now let me start pushing my x value closer and closer to x equals 0. But notice this time I'm coming close to 0 from the right-hand side. And once again, notice how my green height is changing and growing rapidly grows. Okay? And so in that way, once again, it also agrees with our understanding that on this function, 1 over x squared, as we are considering the limits of this function 1 over x squared, letting x coming close to 0 from the right-hand side this time. Okay, then also the green height you notice from my graphical illustration grew to positive infinity as well. And so once again, after that consideration, then we are looking at right-hand side limits came to positive infinity. Left-hand side limits on the same function coming close to 0 from the left-hand side also gave a limit. The vertical height came to positive infinity. So I also explained that positive infinity, even though not being a finite number, not being a definite number, but at least it's a direction where our vertical height is heading to. And since both side limits here headed to the same direction, and so we can also make that final conclusion that, so in the end, 1 over x squared as our main function, it's our ultimate function here, but taking the limits of this function by letting x getting closer to 0, but generally from both sides, this gives us the limit positive infinity as well. And that was our answer that we have seen back in the earlier lecture. Okay? And now let's make our way into, and like I said, I'm not able to go through every example I cover in the earlier lecture, but at least it's illustrative enough with these ideas and how it's showing everybody, anyone viewing this video, about how the numerical estimates of a limit agrees with the graphical estimate of any limits problem. So let's now look again at our example 3. But we only want to focus on part A of example 3. So our function was a piecewise function in example 3. F of x was defined to be, and I only need to quickly recall, and I'm going to have to erase this, but minus x plus 3. It was this one piece right here. If so, f of x is defined to be this piece, this expression minus x plus 3, if we would take any input x less than or equals to 3. And the same function, but will equals a constant 1 if x is taken anywhere above 3, if the input x value is taken anywhere above 3. So again, anyone being enrolled in a calculus class is required to know how to graph and and also required to understand how the graph of any piecewise function looks like. Anyone being in calculus, you are in the beginning door to a lot of fields related to math. So it is your responsibility to understand and to understand what the graphs of these piecewise functions look like, and at least get to know how to graph these functions. So I am going to show you the graph of this function right here. Now that's not the one for it yet, but here is the piecewise function that we're looking at right there. Okay, so when x is being anywhere less than 3, and once again our actual graph is being displayed in red, just like any of the earlier example over here. But for x being anywhere less than 3, so to the left-hand side of 3, 3 is here on the x-axis, anywhere on the left-hand side of 3, our graph was that line of minus x plus 3. But it stops right at x equals 3. And that's the whole idea. And then when we switch the x value to anywhere above 3, then we're going to have our function remains as a constant horizontal line, y equals 1. That's why I have this flat line right here. And that also explains the reason why I have a solid dot here and also an empty dot right here when x equals 3 on that line. But further, the explanation allow me to explain that in an algebra course rather than in this course for being a calculus class. But now let's look at the limits problem here. So back to our problem, this same problem. Hopefully anyone once again took note of the problem we had, because I need to really erase that now. But so we want to, and you saw that through the graph that it has a sort of like a jumping nature right at x equals 3, and unfortunately that's the point where it creates the limits problem for us. So the same function f of x there, too complicated to write it all down, so I'm writing that for short, that same function f of x. I wanted to, or the problem in example 3a wanted us to find the limit of that problem as x was getting close to 3. And once again, this limit point here, we were getting close to 3, but without any superscript indication, meaning it is our responsibility to find out the left-hand side limits and the right-hand side limits, and then make our final conclusion. All right, so let's get ready for that. Okay, so let me now put ourselves in a little closer zoom right here so that we can see how the graph behaves right here. And so in this case, my red point, solid point, also right on the x-axis also happens to be my limit point, so I'm not going to bother blending in that blue point being the limit point on the x-axis anymore. But now from the left-hand side, so I already had an x value, x equals 2, being to the left-hand side of 3. And now I'm going to let that black point, pretending a value on the x-axis, getting close to 3, but from the left-hand side. So notice how our green point is changing. So as our green point is, the green height. So as our black point is getting closer to 3 on the x-axis, the green height is losing its altitude, losing its height, and it looks like it's making its way to drop down to 0. So now we have our reason to conclude that this function, this same function f of x, but now the limit of that function, as we're letting x coming close to 3 from the left-hand side, then this limit, the height, the green height, which is the limit of our function, came down to 0. Okay, and now let's investigate what's happening if we are coming closer to 3, but from the other hand, from the right hand side. So let me move this pointer further out. Now, so on the right hand side, our piecewise function appears to be a constant flat line right here. I'm starting with a value x equals 4 here. On the x-axis, it is to the right-hand side of 3, and now I'm getting closer to 3. But now, being the nature of being a constant function, being a constant piece, is that no matter where you are at, as long as you are to the right-hand side of 3, you are constantly having an output value 1. That's why anywhere I'm moving my black point on the right-hand side of 3, anywhere I'm moving that point to, the green height remains constantly 1. And so now as I'm letting my x value coming closer and closer to 3 from the right hand side, my green height become 1. And it seems like even if I keep getting so close to 3 right here, right there, then it still remains 1. So our prediction was, and notice it could be a little confusing and scary, that the fact that we don't have the point here, and that's the whole idea. Even if we don't have the point there, it's an empty dot right there, an empty point right there. But as we are letting our values getting closer to 3 from the right-hand side, because no matter how close, we're still not at 3. So don't worry, we're still going to have a height being 1 as long as we're still to the right-hand side of 3. See, let me make further zoom like that. See, now we can still tell a little bit that we're still to the right-hand side of 3, which is why we can still have a height being 1. Okay. So now prediction now from the graph through the graph is telling us that the same function, but if we're finding the limit of this function by letting x coming close to 3 from the right hand side, okay, that limit actually turns out to be 1. Okay, and so left hand side limit and right hand side limit did not agree in this case, and that was the reason why in my earlier lecture I was saying that the limit for our function, generally when x came to 3 from both sides, that limit there was a D and E, which stands for does not exist. Okay. And so I'm just going to be very brief on part B of our example 3 here. But example 3, I also introduced this famous function that everybody knows it by heart since your algebra course, 1 over x function. And we want to consider the limit, to find the limit of this 1 over x by letting x coming close to 0. Okay, and keep in mind again, for this kind of function, we have, if we plug in x equals 0 into the function, we have a problem where we cannot divide by a 0 value in the denominator. And so, like I said again, this function has the domain anywhere except x equals 0. So we can take any value and substitute it in as long as the value is other than 0, non-zero value. But see, the problem here is that we need to find the limit of this function when x was coming close to 0. All right, so once again, let me switch over to my graphing screen right here. So here it is, the graph for 1 over x, that famous hyperbolic shape right there. So this hyperbola, left hand side, and let me put it in a closer zoom and blend the two screens together right here. But in a closer view, x equals 0 is right here, that blue point on the x-axis. But notice we cannot have a height because that's the way it is. We cannot substitute x equals 0 into the function, and so we won't have a height that drops right on the function itself. And by the way, again, the red curve is the actual graph itself. So now getting close to 0 from the left-hand side, and here's observe my motion of the black point right here. So the black point is indicating a value on the x-axis. Getting close to 2. So from the left-hand side, and it looks like if I'm getting close to 2 from the left-hand side, then my green height, the vertical height of the function or the output of the function keep dropping down to negative infinity. And that's how it's explained graphically right here on the screen. And so once again, here's how it agrees with what we've had earlier in our earlier lecture. But this function, okay, the way we formulated that, as we were letting x getting close to 0, but from the left-hand side, this function came to a limit, meaning those vertical heights drops down to negative infinity. It's heading down in one direction. Okay, and on the other hand, as I was getting close, and I also believe that when I was going through this example myself in the earlier lecture, when we were still numerically estimating these limits, and I also had a little bit of the graphical explanation of this graph already, but here it is. We can explain again. But now as I'm coming close to 0 from the right-hand side, and you can see that my height, my green height, indicating the vertical, indicating the function output is growing higher and higher and higher, and growing to positive infinity, so in a completely opposite direction. And so I can also make my conclusion that this function 1 over x has limits when x come to 0 from the right-hand side. This function has limit equals to positive infinity. And so now once again, the two-sided limits did not agree in this case. That was the reason why 1 over x. And taking limits as x coming close to 0, but generally from both sides, the answer must be a D and E, which stands for does not exist.